So this is called the dominant pose. The dominant pose, that is the location of the pose closest to the origin here. The dominant pose basically is corresponding dynamics in time domain basically will dominate the system dynamics, which means the dominant pose corresponding is the slowest dynamic components of the system. So here, basically, if you like, you can say here we circled that is the corresponding dominant pose of the system. Are we good? Okay, so here let me give you a little bit more introductions here. So that is the complex plane again. Okay, so for example, if you have proceeded the similar analysis and then corresponding to each term, you can locate the location of the poles. And so say here we have the locations, and these regions basically is the clusters of the dominant poles. So where they located, maybe on the real axis, maybe simply a complex conjugate. Okay, so basically this is the region. You simply use your justification to make a line. Okay, and this one, basically this region is for, we call the non-dominant insignificant, significant poles. Insignificant poles corresponding, just like this case, they corresponding to the faster dynamic components. Insignificant, that means their influence to the determination of the system dynamics is small. Okay, so basically that corresponding is those poles correspond to fast dynamics. Okay. So under which situations in the follow-up we might be able to ignore those things, which means approximate those dynamics, get them equal to 0 without influence this one. As long as you can determine the distance here, it's called the D. Okay. And D can be, as long as you can pretty much say using rulers to define a gap, and the gap basically is about 5 to 10 times of, let me call this value, so say let me call this value here, and say let me call this value is alpha. It's alpha. Okay, so basically we get a one, if we can make a very clear cut of the two clusters, and which separated by an order of magnitude of these dimensions, then all the poles here we can approximate, get them away. So that means under that situation, we might be able, if say I equal to 1, I just make numbers, okay, to 10. And out of the 10 terms, you might be able to drop off the 9 terms and leaving 1 term that is in the dominant range. You know what I'm saying? And the same thing here is say I equal to 10 to 10 times. And maybe of this group, they have 2 terms that falling into the dominant range, then you can simply drop off the other 8 terms. Okay, when we drop the terms, simply we will reduce the system orders. We will reduce the system orders, so that is called the system simplifications. Okay? And we may look at one example here. Let's see. Here in this section is pretty much more like conceptual, but here we can try to see one example here. So we consider third order systems like this. Okay, so here we have a closed loop systems, and before we do anything, we can try to plot the poles here. So these are real S and imaginary S, and we have simply conjugate poles, so that is -10 and -1 plus J. Okay, we have the 3 poles here. So let me label the poles exactly. So this is the 1. So that is here and here. And this is -1 here. Okay, so we have 2, and the other one is here, and that is located 10. So under these situations, you can see we have a 2 range approximately. Okay, so I just draw it. So from here you can see this is the range that basically fit into our discussion there. So right away we can identify this pole is not important in determining the system dynamics. We can drop it. Drop it, that means the system will be able to, we can approximate this 3rd order system by a 2nd order system without distorting the categorization of the system too much. Okay, got it? So that's the concept. And how to do it correctly. And so therefore the first one, so this 3rd order system can be approximate by a 2nd order system by dropping the insignificant pole at s equal to -10. We can approximate, so which means we can reduce the orders and without with very good approximation. And how to do it? And now the issue is how to do it. We can give a try, and before I give you the systematic way, probably we will talk about that one next time. But we can give a trial this time, okay? And how to approximate if you simply approximate equal, you simply approximate this one, just how to say, scratch it. Okay, so that means the term will be heading something like this, right? So you try to approximate by directly scratch this portion away. What happens? If you try to approximate that equal to 1, it seems not good. Why? I tell you why. So this is not good. Why? You can see, for this term, you're going to drop. Let me use this different color. For this term, for the term you like to drop, you basically evaluate its corresponding magnitude at the dominant pole here. So S plus 10 is magnitude. Here I at S equal to -1 plus J. So this is our dominant pole. You calculate its magnitude. And in terms of magnitude, if you remember, this is A plus Bj, and its magnitude simply is equal to A squared plus B squared. Right now we're doing the complex algebra, okay? So here you calculate this one. This one pretty much is equal to 11 squared plus 1 squared, that is about 10 something, 10 point, say 10.1, okay? You see, at the dominant poles here, you try to approximate 10 by 1. It's not good, right? Because if we try our intuition, we try to cover this term, basically you implicitly assume this term approximately equal to 1, right? However, the value of this one at the dominant pole basically equal to 10. You cannot do it because that basically conflicts its natures. Okay, the best way is this. We do the trial two. Is this y over r? Okay, and now we know we are trying to approximate this term equal to 1. Okay, keep that in mind. So why not? We're doing is this. We simply have the s divided by 10 plus 1. We simply reform this one, get into this. Okay, and the reason why is this, we can, again, we calculate the magnitude at s equal to minus 1 plus j. This term, if you do the calculation, this one is approximately equal to 1. And that is a good one. Okay, so if we want to do this one, then we keep writing this, and 2s plus 2. So here in the whole denominator divided by 10, so numerator must be divided by 10. So after the approximations, because right now this one is pretty much equal to 1, is a good approximation, so this one will be equal to s squared plus 2s plus 2. This is a good approximation. If you approximate the second order system with 20 divided by that one, then basically you will introduce unnecessary scaling mistake. Think about this one. Again, the key, the essence is try to make sure the term you're going to drop, the magnitude is equal to 1. Okay, try your best and to treat the whole system such that that term will be approximately equal to 1. That is the essence. Okay, and for how to do that one, that will be depends on the case by case, but that is the real the situations. So coming back on Wednesday, we will have more systematic way to do the reduction of the system orders. Okay, and there we will be clear about the process.